To extract a clean target signal from a chaotic mix of high-frequency noise and low-frequency drift, engineers route the raw feed through a filtering system. Mathematically, we represent this system's architecture as a transfer function, g of s. To evaluate how it responds to different frequencies, we substitute the complex variable s with j omega. The engineering challenge is that omega spans a massive, continuous spectrum. We have to evaluate how this exact system architecture reacts to inputs ranging from near zero to tens of thousands of radians per second. Calculating the exact magnitude and phase shift point by point across that massive range requires an exhausting amount of arithmetic. Worse, staring at a table of calculated complex numbers offers zero intuitive physical insight into the system itself. We need a method that bypasses brute force calculation, allowing us to instantly visualize how an architecture will filter signals before a single component is built. The solution is the Bode plot, a dual graph representation that plots a system's magnitude in decibels and its phase angle against a logarithmic frequency axis. The mathematical power of this approach comes from that decibel calculation. By defining the magnitude as 20 times the log base 10 of the absolute value of j omega, we exploit a basic property of logarithms. A transfer function is usually a fraction made up of multiplied and divided complex terms. But when wrapped in a logarithm, that complex multiplication expands out into a series of simple, independent terms added or subtracted together. By converting multiplication into addition, we can construct the frequency response of any linear time-invariant system simply by stacking basic geometric shapes. Because of logarithmic addition, every LTI system, no matter how intricate, can be decomposed into a finite set of fundamental building blocks: constant gains, simple real poles, and simple zeros. This chart shows the standardized asymptotic magnitude traces for these blocks. Notice each block is governed by a specific break frequency. The trace remains a flat 0 decibels until it hits that corner, transitioning into a predictable angled slope. This second table maps the corresponding phase contributions. They are equally standardized, shifting predictably between specific angle values, stepping up or stepping down, based on those exact same break frequencies. These straight-line traces act as a genetic code. If you know the basic traces, you can predict the physical behavior of any system architecture. Let's apply this to a simple control system, with the transfer function g of s equals 10 divided by the quantity s plus 10. The vital first step is converting this expression into the standard Bode form. By dividing both the numerator and denominator by 10, we properly isolate the constants. Now we can clearly identify the individual parts: an overall gain of k equals 1, which translates to 0 decibels, and a single simple real pole dictating a break frequency of 10 radians per second. This graph maps out the individual components. We have our constant 0 decibel line for the gain, and the trace for the real pole, which drops off into a downward slope exactly at 10 radians per second. Summing the individual traces vertically generates the final asymptotic Bode plot shown here. Looking at the combined blue line, the physical implication is obvious. The flat 0 decibel slope allows low frequencies to pass unchanged, while the downward slope aggressively attenuates higher frequencies. The addition of standard traces visually proves this function operates as a first-order low-pass filter, an ideal architecture for killing high-frequency measurement noise. Let's scale up the complexity and evaluate a multi-factor system. Here, the transfer function is 10s divided by the quantity s plus 1 times the quantity s plus 100. We immediately convert this complex equation into standard Bode form. By isolating the constant of 100 in the denominator, the math yields a clean formula ready to be broken into its base properties. We extract 4 distinct components: a negative 20 decibel gain, a 0 at the origin, and 2 simple real poles. The 2 simple poles explicitly dictate our critical break frequencies. The first acts at 1 radian per second, and the second acts at 100. No matter how intimidating the initial transfer function appears, standardizing it always reveals a simple inventory of individual parts, ready to be stacked. This top graph plots all 4 individual magnitude contributions. The solid blue line, the 0 at the origin, generates a persistent rising slope across the entire band. The green and pink pole lines activate later, each introducing a downward slope at their respective break frequencies. Here is the final superposition. Adding these distinct slopes vertically traces the overall dotted asymptotic response. Initially, the zero's positive slope drives the trace upward. Between 1 and 100 radians, the first pole's negative slope activates, perfectly canceling it to create a flat plateau. Through the mechanics of logarithmic addition, we've instantly mapped the geometry of a complex system without calculating a single specific point of data. This chart displays the asymptotic approximation in dots and the continuous magnitude response as a solid line. Notice how closely the actual response hugs our approximation. In the low-frequency region below 1 radian per second, the trace rises steeply from a heavy negative gain. The extreme low gain in this region means the system acts as a differentiator. It will heavily suppress slowly varying inputs like DC offsets, sensor drift, and gradual environmental disturbances. Moving to the mid-frequency region, between 1 and 100 radians per second, we now carefully evaluate the horizontal plateau. The amplitude here rests at -20 decibels, meaning the output is reduced to 10% of the input. But because this gain is flat, all frequencies in this band experience identical attenuation. The signal shrinks, but its core shape suffers minimal distortion. This mid-frequency plateau functions as the passband, preserving the integrity and waveform of the target signal. Finally, looking back at our chart, we examine the high-frequency region, above 100 radians per second, governed by the second pole. The magnitude goes into a sharp downward dive. The lower phase plot shows a drop toward -90 degrees. While the system introduces a phase lag here, the delay is highly predictable. The steep magnitude roll-off provides a critical engineering defense: the aggressive suppression of electromagnetic interference, switching noise, and sensor artifacts that plague these higher frequencies. Consolidating these three regions provides our exact operational profile. The architecture rejects low-frequency drift, securely passes the mid-frequency signal, and rejects high-frequency noise. This describes a textbook bandpass filter. The Bode plot is a direct visual translation of a system's architecture. It empowers engineers to instantly see exactly how a mathematical transfer function will shape and command a physical signal in the real world.